Thank you all for coming to the Tufts Energy Conference. We are excited to be here with all the distinguished scholars as well as all the participants. And this panel is called Scaling the Next Generation Energy Solution, the Nuclear Approach. Please note that the whole webinar is being streamed on Zoom and will also be recorded. We would also like to extend our appreciation to the Hitachi Center of Technology and International Affairs for making this panel possible. This panel is also part of the Hitachi Center speaker series. There will be time at the end for our discussion for the Q&A, and also remote participants are welcome to place your questions in the chat.
So the purpose of this panel is to talk about nuclear energy and kind of how it relates to scaling next generation clean grids. The big question is, how do we scale those grids while retaining reliable generation capacity on the back of technologies like wind and solar? So one of the big approaches to gaining a lot of traction is nuclear power. So we want to explore the challenges of scaling next generation grids, the role nuclear can play, and the issues that it has. So allow me to introduce our moderator, Francesca, Giovannini, Adjunct Assistant Professor for International Security here at the Fletcher School. She's also the Program Director for Global Security and International Affairs at the American Academy of Science and Sciences, and also an associate to the project on managing the atom at the Belfer Center for Science and International Affairs, and as well as an affiliate Center for International Security and Cooperation Stanford. So, Professor, you would like to introduce our panelists.
Thank you so much. I'm actually at the Belfer Center Harvard Kennedy School right now. The American Academy was my previous position, but thank you, Ryan. I really appreciate it, and thank you so much for coming, everyone. I think it's incredibly timely to have a conversation about nuclear energy and the role that nuclear energy can play in a decarbonized economy. Of course, nuclear energy can be quite politicized as a topic. People have strong feelings pro or against it. And I think we want to understand a little bit more about what are the promises of this technology, the advancements that they've made, and also some of the challenges that still remain. And I cannot think of two better panelists, Luisa and Jacopo, to speak about this topic. Now, we've all joked that there are 3 Italians sitting here. Italy failed twice to vote yes in favor of nuclear energy. In fact, it's probably one of the few countries that could have nuclear energy and doesn't. But I can guarantee you that our specialists and experts are really top notch. So let me introduce first Jacopo, Jacopo Buongiorno is a TEC professor of nuclear science and engineering at MIT. He is also the director of the Center for Advanced Nuclear Energy Systems and the director of Science and Technology of the MIT Nuclear Research Reactor Laboratory. He has published over 100 journal articles in the area of reactor safety and design, to phase flow and heat transfer and nanofluid technology. I'll stop there, but I want to say you have gazillion other affiliations that are really extraordinarily impressive. Professor Luisa Chiesa is an assistant professor in the Department of Mechanical Engineers at Tufts University. She has done a lot of work, and I want to include also your work on sustainable development, sustainability in general, which I think is really pertinent to some of our students here. You have been in this field for over 10 years. You've done a really impressive work on superconducting materials for large-scale applications. You've received a PhD from MIT, and you also have a bachelor degree in physics at the Università degli Studi of Milano. And you have had really extraordinary affiliations. I want to cite in particular the Lawrence Berkeley National Laboratory, and you are also a guest scientist at the Fermilab National Accelerator Laboratory. So I want to begin with a very fundamental question for you today. There seemed to be a very brewing enthusiasm about the nuclear field today. And there is this new catchphrase, which is we are living in an age of advanced nuclear reactors. Jacopo, can you explain us what makes these reactors advanced and different from the traditional ones we have seen before?
Yeah, so brief maybe introduction to set the stage for the answer of the question. So a nuclear reactor is a heat source, right? So it uses a nuclear reaction, which is called fission, to generate large amounts of heat. The vast majority of the reactors that we've been operating, either in the United States or international for the past 60 years, are large. They generate a lot of power, okay? So they're typically 1,000 megawatts electricity output. Now, I don't know if you have a sense for these numbers. 1,000 megawatt is enough to power a city roughly the size of Boston, 750,000 households. Okay, so that's traditional. And they are cooled. There is a fluid that circulates through the reactor core to remove all that energy and then do something useful with it. They're cooled by simple water, H2O. So they're called light water reactors. Now getting to the answer to your question. The two trends that we're seeing in terms of advanced technologies essentially go the following way. First, the industry is interested in shrinking the reactors, not these big machines, because there are lots of challenges in building large machines. And also there are markets that require a lot less power than 1,000 megawatts. Okay, so for example, there are a lot of coal-fired plants out there, natural gas plants that will have to be replaced if we're serious about decarbonizing. And they're not 1,000 megawatts. So what do you replace them with? Maybe with a reactor or nuclear power plant that is only 100 megawatts. So going down in size is a trend that we're observing. And then the other one is replacing water as a coolant with a fluid that allows you to operate at a higher temperature, much higher temperature. So if you have water, you're basically stuck at around 300 degrees C. If you use, for example, a gas like helium, or you use sodium, you use a molten salt, you can go up to 500, 600, 700 degrees C. Now, why do you think it's important to operate at a higher temperature? For two reasons. First, the second law of thermodynamics says that the efficiency of conversion from heat to electricity, which is very often what you want, is higher if that heat is produced at a higher temperature. You guys remember from high school the Carnot cycle? If you do remember, then you know what I'm talking about, okay? So you have a higher temperature reactor is a more efficient reactor. Number two, you have customers that don't necessarily require electricity. They want heat and they want it at a high temperature because they are using a process. This could be a chemical process, it could be a manufacturing process, whatever it is. Think about making steel, think about making cement, think about making some chemicals or whatever that requires heat at that high temperature. So those are the two big trends. So when you hear the word advanced reactors, these days what that really means is a little bit smaller typically, and a different coolant that allows you to operate at a higher temperature. Let me stop there as an intro.
Luisa, let me ask you, and I know you have also strong views about this. So size and efficiency, but of course, we know that one of the biggest challenge for the acceptance of nuclear energy is the question of safety. How more safe are these reactors? If we shrink them, if we make them more efficient, how does the safety question play?
You want to go? Yeah, go for it.
And you can add. I'm more. So my background is more about fusion energy.
Yeah, I have a question.
The opposite, and you fuse together atoms, and it doesn't exist yet, so to speak. And we don't produce any electricity so far. But regarding these advanced reactor, one of the big advantages is that they are inherently safe. So they have, most of them have some kind of passive system associated with them, and so you don't have the catastrophic events that you might have experienced in Fukushima or Chernobyl or Himalaya because of the way they are designed. They usually use fuel that it's maybe in a pellet form. And so they have several layers that are constructed around the radioactive material that allows you to go to this higher temperature, but at the same time being able to stop the reaction in case it's necessary. And so that's another big advantage of these advanced design reactors.
I think Luisa said it right. Certain classes of accidents like Fukushima, 3 Mile Island, Chernobyl are essentially eliminated by design. That does not mean that accidents are impossible. Okay? Any machine designed by mankind can fail. And so even these advanced reactors can fail. But the question is, what are going to be the consequences of those failures? They're going to be a lot more benign than with the traditional reactor designs. And so that's the value proposition in safety space. Having said all of this, and I know that you and I discussed this a few years ago, even the existing fleet, which is old technology, is exceedingly safe. Okay, so there are continuous reviews, upgrades. The Nuclear Regulatory Commission inspects these plants continuously. And so this is a very, very safe industry. But it's striving to become even safer, which is great.
So I want to bring a geopolitical element into play here, because of course, the biggest nuclear technology exporter so far has been Russia. And some have criticized the Biden administration for not putting, for example, Rosatom under sanctions. My understanding is that the development of these advanced reactors is based on a production of a specific fuel that right now only Russia can produce. Is it correct? And if Russia, can no longer export, then what do we do?
Are you going to triage the questions?
Yes.
You want me to start?
Yes.
Okay. So the type of fuel that you're referring to is called HALEU, which stands for high assay low enriched uranium. So uranium is a naturally occurring material, and it's primarily made of uranium-238, the isotope 238. That's over 99%. But in fact, what we use as fuel for reactors is the isotope 235, which is only 0.7%. Okay, so in traditional reactors, in order to make them work efficiently, you need to enrich, as we say, the concentration of uranium-235 from 0.7% up to, say, 5%. Okay. Now, if you keep going with that process and you enrich it to 95%, what do you think you have? Now you have weapons-grade uranium. Now that's material that you can actually use for nuclear bombs. Okay, we don't want that. So there is an internationally acknowledged definition of what constitutes low enriched uranium, and that's less than 20%. Okay, so you can go up to 20%. People will not ask too many questions. That's oversimplifying, but let's say that. Let's put it down. So now, we currently have facilities in the United States that can go up to 5% because that's all the fuel that we've ever used or need. Okay, but these advanced reactors that I talked about, these that are a little bit smaller, that go up in temperature, et cetera, are designed to use uranium that is between 5% and 20%. So we need to develop and upgrade our enriching facilities so that they can go up to 20%, and of course doing that safely. At the moment, to your point, the only country that really has a commercially available HALEU is between 5 and 20% is Russia. But the US government is working very, very hard, and put, I think, about $1 billion, is probably not, as part of one of the recent deals, into upgrading our capabilities so that you can basically produce that. I don't know if you want to add anything.
Yeah, no, I think it's I agree. I have to say I'm biased. I do believe that the nuclear industry is very safe, and I do believe that we can achieve what is required out of the electrical power systems. And it's a matter of refurbishing the industry, because in the US, we haven't built a reactor. I think there is a new reactor that is opening up in a year or two, and we haven't built a nuclear reactor since the 70s. And so that's a big challenge, because we forgot how to do things and we don't have the infrastructure in place for that.
Yeah, I agree. Let me just add. So there are no technical challenges in making that fuel. It's just a matter of upgrading the facilities that we have. This is not research and development. Enriching uranium has been done for good reasons and also for bad reasons for 70 years. So the technology is known. It's just a matter of upgrading. So
I have a question for you specifically, Luisa, about the grid. Because one of the big questions that we hear often is, well, okay, we have all this, the explosion of reactors all over the world. We have all these reactors in Africa, in India. But
let's not say the word
explosion. I know. It was a very unfortunate. But so you have, the really, the ability of creating a real global market for these reactors. How should we think about the grid?
Right. I think the grid is even more challenging issue, if you ask me, because the infrastructure in the US is very old. And so if we really are serious about electrifying everything, everyone wants to electrify everything. And one of the big obstacles is, yes, we can build new reactors, we can build new power plants, but then you have to have a way of transferring this electricity. And right now, the infrastructure in the US, if you look at a map of the grid, it's amazing, an amazing mess. And so I think it's not a sexy topic for a lot of people. And even when I teach my classes, the students never think about that aspect of, once you produce electricity, how do you actually transfer it everywhere? But an idea of this small reactor is also simplifying that. And so a lot of these advanced reactors are designed so that it can be also modular. And so you need one small one and you have less of an infrastructure associated with that. But I think more investment should be done on the electric. At least I think that should be a priority.
Let me make a comment on the grid also. Electricity is an awesome form of energy, right? It's very, very handy. How has improved our lives, so to speak. And so the grid certainly has to grow, and we can electrify a lot of things. But we cannot electrify. You cannot electrify, realistically, you cannot electrify air travel. You cannot electrify ships. You cannot easily electrify some processes like the production of concrete, steel and things of that. Although now there are some startups that are trying to do some processes to do so. So the point is, we're not just going to need the grid. We're not just going to need electricity. We're going to need a lot more energy in other sectors to displace fossil fuels, which are currently meeting the energy needs of those sectors. And one more thing to keep in mind is that if you look at the pie chart of the CO2 emissions or greenhouse gas emissions, only at the moment, only about a quarter of those emissions are associated with the production or generation of electricity. 3/4 are in other sectors. So we need to tackle all sectors of the economy, not just the grid, because even if tomorrow, snap your fingers, and CO2 emissions are eliminated completely from the grid, you got still 75% of the job to do.
Yeah, so it's, you have to think about agriculture, you have to think about manufacturing, and the steel and the cement industry are
building,
gigantic.
Transportation.
Right, and so, yes, it's a complex problem, and so I think people should be realistic that it's not gonna happen overnight. And we like it or not, I think petroleum and coal and fossil fuel they have to play a role for a little longer. We cannot just simply say forget about them and do a complete switch.
Yeah, liquid fuels are high energy density. That's why they've been so popular, because they're so easy to move around and utilize. So in fact, just one last comment and we move on. When we talk about decarbonizing transportation, air and sea, one approach that I think has merit is to actually produce carbon neutral drop-in liquid fuels that look chemically identical to the fuels that that these sectors use now, but they are made in a carbon neutral fashion, which means you have a carbon feed that either comes from capturing CO2 from the ocean or the air, or from biomass. Okay, because that's then a cycle. So I think that deserves.
Yeah, they actually have a panel tomorrow at this conference.
Oh, they do. Okay, great.
About fuel. Wonderful.
Yeah.
So two other issues that I would bring up if I were skeptical of nuclear technology. First one to me is, okay, you end up having all these reactors around the world. I have a student who actually is interested in what happens to the question of transportation. Will you have ships transporting, fissile material around the world in order to power these reactors? Would you have more fissile material being transported on roads, right? How would this increase the risk, for example, of displacement, of potential, terrorist sabotage, things like that? So the more we increase the number of nuclear reactors, the more we increase the risk that this material falls in the right hands. How is there, do you think, an answer to this?
Maybe I can start. So I got news for you. In the US, we move fresh fuel and spent fuel around all the time. Just in the US alone, I think there have been transferred, like 7,000 transfers of spent fuel, and without a single accident. So an accident can happen, okay? So, but the experience has been exceedingly positive. Okay, so it's, again, from a technical point of view, it's not right. But you ask a very good question. So, what are the opportunities for diversion and what can people do with that? Okay, so when we talk about fresh fuel, which means either 5% or 20% enriched, yes, we don't want that to fall into the wrong hands, but what the heck are they going to do? It's not weapons grade. So and it's actually not even radioactive. Right, it's uranium, so you can hold it. I can massage my arm, and nothing happens.
Don't try it at home. Sure.
So that's not particularly exciting material to get your hands on. Spent fuel is highly radioactive. It comes out of the reactor. Okay, and there is a little bit of plutonium, but you know very well, in order to extract that plutonium, which would be weapons grade, that requires a heavy-duty industrial facility with chemical separation. All that. That's not a terrorist group level endeavor or effort. The only residual sort of use that some ill-intentioned actor could make of that material is to use it for a dirty bomb. So you have some radioactive material, you strap it around a piece of TNT or some explosive, you throw it out on the square, it's going to disperse a little bit, people panic. Okay. Now, these studies have been run over and over again by national labs after 9/11, et cetera, et cetera. If you're close enough, you're going to be taken out by the bomb. It's not the radioactivity. And radioactivity doesn't, the kind of nuclides that you would strap on, they don't actually disperse very easily in the atmosphere. So also the radiation effect, the radiological effect. So doesn't keep me up at night. There are other issues. We can talk about waste. We can talk about, we can talk about cost, right? That's important. But frankly, this idea of moving around material. So that's my opinion. I don't know if you
completely agree with that. I think it's one of the least. It's not easy, as you were saying. It's not easy to get the material from a nuclear power plant and make a bomb out of it. So I think it's a misconception of yeah. And we worry about transportation. You look at the incident in Ohio of an explosive chemicals. It may maybe make more damages than any uranium transportation. And so I feel like the nuclear industry has this bad reputation. Yes, it's unfortunate that we had three major accidents that were pretty bad, but if you look at the rest of the industry, I think they're not as scrutinized as nuclear.
Yeah. So I want to talk about, so normally, I would say, and correct me if I'm wrong, but there are three arguments against nuclear energy today. One is the question of nuclear safety. People look at Fukushima, they think, gee, I'm not sure I want to take that risk. The second is nuclear waste, right? Like we are basically leaving a legacy, a terrible legacy of toxic, material for generations, for thousands of years. And then the third one I would say is cost. Is the idea that these reactors right now are horrendously expensive. And if you don't have, a state capital like Rosatom or China, Atomic Energy Commission, you are not able to access these technologies. So I wanted to ask both of you, these advanced reactors, do they help solve or at least near us to some solutions, especially to the question of nuclear waste and cost?
Let me start with cost. Okay. The answer is we don't know. The theory is that they're smaller, they're a little bit simpler design. So hopefully the industry has learned from recently completed or near completed projects which were badly over budget and badly beyond, delayed. All the issues that we have observed were related to management of a large construction site or the immaturity of the supply chain or regulatory system, which is not particularly streamlined. It had nothing to do with the technology itself, but the reactors and the materials. All that is sort of plain vanilla. We know that. So will this new wave of smaller reactors cost less? Well, in absolute terms, yes. I think they will cost less. Per unit energy generated? Question mark. Time will tell, okay? Once we start building a few, operating them, then we'll see if they're cheaper than what we've seen before. But at the moment, it is a question mark. I can't tell you with a straight face. I'm sure that it's gonna be cheaper and therefore very competitive. On the other hand, going back to, I think, what you were saying earlier, or maybe you were saying earlier, when you look at an integrated energy system, like the grid, and you're gonna have some intermittent renewables, solar and wind, which are great, we should have more and more. You do need energy sources like nuclear, which are carbon-free, but also dispatchable base load. Because if you don't, you try to completely decarbonize your grid with solar and wind plus storage, then you end up overbuilding the capacity of solar, wind, and storage to the point where the cost of the grid, let alone the reliability of the grid, are going to be abysmal. And so even if on a per unit, say per kilowatt hour, the cost of nuclear might be higher than the cost of solar and wind, when you plug it into an integrated system, it actually lowers the overall cost of the energy itself. So that's how I look at it. You want to take the lovely waste?
I think, yeah, well, the cost is a problem, but, it's always maybe societally, we have to decide what we put value on. So if we really want to solve carbon emissions and whatever, then we invest money and there is no escaping. But I agree, there is no number And the waste.
Can I make one more comment? So since we are on cost, though, the important thing to keep in mind is the cost is an issue in the US and Western Europe. It's not an issue. The cost of new nuclear is not an issue in countries that have been continuously building nuclear power plants. I'm thinking South Korea, I'm thinking China, I'm thinking Russia, even now the Middle East where they started and all of that. In those countries, we see projects being delivered completely on time, basically, and on budget. Okay, so the issue has really been in the West. We have completely lost, I think you made this point, we're completely lost the know-how on how to build these big machines. And so now we are at it with smaller machines. Maybe we'll go better, we'll see.
So what's the cost in those other countries?
So in China, South Korea,
what's the cost?
Yeah, what's the cost? So I can tell you, these numbers are public. They're not always easily verifiable when they come out of countries that don't have sort of the same transparency in numbers that we do. But in China, South Korea, they routinely come in at around $2,000, $2,300 per kilowatt installed. That's pretty darn cheap. That translates to something like $40 per megawatt hour. Okay, so that's pretty ridiculously cheap energy because it's, again, CO2 free and dispatchable. You can't do the LCOE comparison with solar and wind because it's not a fair comparison. That's what you're doing in your mind. But anyway, those are the numbers. Here in the US, if you look at the project that I think has been mentioned a couple of times that we're finishing now, the infamous Vogel project in Georgia, which every month seems to be delayed by an additional month. And so we're almost like asymptotically getting there, but we're not getting there. It's probably going to be around $10,000 per kilowatt. So disgustingly expensive. It's a regulated utility, so they'll recover the cost anyway. But clearly that wasn't a very successful project.
So tell me a little bit about the innovation on waste. If is there innovation that you think might be promising?
I don't think there is. No, frankly, no, because
it's not a problem.
No, because it's right. Because I would say that it would be the wrong focus to have for an advanced reactor. So there are ways in which you can take what we call waste. So let me take a step back because otherwise people don't understand what we're talking about. What people call waste is the spent fuel. So you got these uranium fuel assemblies. They go into the core. They stay there for a number of years, and then they come out. What did they look like? They look almost identical to when they went in, except that within the rods, what has happened is that some uranium has broken up. That's what we call fission, and it's turned into these fission products. Those fission products are radioactive. And so once that fuel comes out of the reactor, it is very, very radioactive. Okay, so that's what we call waste. It's not green goo that is spilling out of a barrel. It's nothing to do with that. That's the popular image that people have in their mind. Couldn't be further from the truth. They're highly engineered, solid rods that come out of the reactor. Okay, so what do we do with that? First, you put it in a pool. They cool down for a couple of years. So radioactivity goes down, decay goes down. And then you move them from that pool into what we call dry cast. These are cylindrical canisters made of steel, a little bit of concrete surrounding. You put them in there, and then they basically sit outside. They sit outside in a parking lot. Like, you know, I take my students to the Pilgrim Nuclear Power Station. They got dry casts sitting out there, and they're just cooled by the air, the atmosphere. That's your nuclear waste, okay? So technically, you can continue to do that for a long period of time, but at one point, you want to put that material underground in a permanent repository. So where the US has failed, but other countries are succeeding, is to identify a location within our big United States where to put these casks finally underground permanently. So, you know, sort of out of sight, out of mind. So we have failed at doing that. Other countries like Finland, Sweden, maybe France, also your study states, right? We'll get there much sooner. I think for Finland next year. Next year, they open their repository. So there are technical solutions. But even in the United States, where we don't have that permanent, that final solution, so to speak, it's not a crisis. That waste is sitting there, and it can be there for a century. Then you put it into a cask again, it can go another century. I hope that we don't have to wait that long. I hope that we find a repository sooner, but it's not something that, again, has created much of a crisis. It's not even expensive, frankly.
It's the long-term issue of the radiation. But if you think any technology, everything we make that then is disposed, it's sort of waste, right? And so if we scale up, wind, and if we scale up solar, you will have some other waste stream that, right? And so I think in that respect, nuclear has a very small footprint when it comes to how much energy you generate per square mile, but also how much waste you produce.
Yeah, and in fact, to go on with that point, which is very important. So the other thing I forgot to say is that volume, the amount of materials that is produced is very, very small. So think about this. You will remember this because it's an easy factoid to remember. So if you were to use only nuclear energy throughout your lifetime, the amount of that spent fuel that you would leave behind all your life, whatever it is, 80 years, 90 years, would fit in this cup. That's the spent fuel that you have used throughout a lifetime, okay? Why do you think that's the case? Why so little? It's because the energy density of uranium is astronomically high, okay? Because it's a nuclear reaction, it's not a chemical reaction. You're not breaking bonds at the electronic level, you're breaking them at the nuclear level, so it liberates millions of times more energy per fission than per combustion of carbon or gases. So tiny amounts of waste.
I have now a very political question, which has nothing to do with your technical knowledge. So we've seen, I think the Ukraine war, and my students know this because I mentioned it several times. The Ukraine war has revealed how nuclear power plants can become a serious military liability, right? I mean, what Russians is doing around the Zaporizhzhia nuclear power plant, the behavior they had on Chernobyl. How much do you think this has damaged a little bit the prospects of serious investments for other countries might live in like unstable regions that think, oh my God, these power plants can become a serious target?
If it has damage, we haven't seen it. I mean, the support for nuclear, whether it's in the US or in Europe, in terms of policies allowing it, countries committing it. I mean, if you think about Europe, which is right there, right? You now have a dozen countries that not only have said, okay, we keep the nuclear plants that we have, but they have declared that they want to build more, right? So you got France, Sweden, Hungary, Finland, Czech Republic, Romania, Bulgaria, Poland. Poland is a newcomer. They don't have it, but they want more, right? UK. So far we haven't seen but I agree with you. It's worrisome that the Russians are using installation to hide weapons and things of that type. So it's become a sort of a pawn in a political scheme.
Yep. Before I open up for questions, to prepare your questions, I wanted to ask one question to you, Luisa. Could you tell us a little bit about, we hear on the news this breakthrough about nuclear fusion, and every time, it's breakthrough. And then when we talk to scientists like you, they say, well, it's not really that big deal. So could you help us think through what are the challenges, and how far are this, with the meaning of these breakthroughs that, are announced?
It's how much time. So there are two ways you can do fusion. So fusion is the opposite of fission. Fission, you break heavy atoms in two. When fusion, you fuse together two atoms. And big advantage of fusion is that you don't have the issues with fuel that can be used for bomb, and you have very little waste that has a decay time that is much faster than fission. And so there are clear some advantages with fusion, but it's more difficult to fuse together two particles and break something that is heavy apart. There are two techniques you can do, is either inertial confinement, and where you use a very complex laser systems to kind of point a lot of energy in one single point, which is what made the news 2 months ago. Great achievement, but if you ask me, that's a technology that is way behind the other technique that is magnetic confinement, where you use large magnets. That's where the superconducting materials come in play. That allows you to confine a plasma, which is charged particles, and you confine this plasma going around this chamber, and you have the fusion reaction, you extract the heat, and then it's a conventional power cycle, like you boil water and you do the conventional power cycle on the other side. The challenge is, to me, especially for the magnetic confinement fusion, is that the type of investment in the last 30 years haven't been as much as maybe other technologies, or there hasn't been a lot of progress. And now there are some startups that are energizing the, no pun intended, the field. And there is a spin-off from MIT that has been doing some great progress in the last 3 years. And one of the main reasons why they're doing progress, it's not because they invented something revolutionary. They were really good at receiving money to do progress quickly. And so now if you look at their timeline, they think that they're gonna have the first experimental reactor not attached to the grid in 2035 or something like that,
2025.
That's the demonstrator.
Spark,
yeah.
that's
Yes.
2 years from
But
now.
it's not like
No, it's not for
producing,
power
right.
production, right?
If you ask me, that's pushing, but it's the first time that I believe that I can say maybe it's not, maybe I can see fusion by the time I'm old or retired. And so there have been some very, very interesting progress. Did they solve all the problems and the technology aspect of it? Maybe not, and then maybe they will have some obstacles as they move forward, but the type of increase in excitement and investment and progress that they've made in the last few years makes me very, very hopeful after a long time.
Could I ask also a follow-up question, since the subject is about scaling? So after you get this very first reactor, how quickly do you think you would be able to scale up to, not maybe to the level of nuclear fission, but
in a way, it's a different way of making heat. So it's not really, the infrastructure doesn't really change dramatically. You don't need any special equipment. It's different technology, but yes, the scale up will be challenging, but I would say it could be challenging for any technology that you're trying to scale up at the level that you want to scale up.
But do you need those big power plants like you need in fission? I mean, is this
no,
the
they can also be modular. It's the same concept. You can have something that is small or sized for 100, 200 megawatt like power plants, and you can string them together and make a bigger one or smaller one. In that respect, a lot of the conventional power generation systems translate into, so you will see some presentations of a typical power plant, and they remove the coal and they plug in a tokamak machine, which is a fusion machine, and they say, oh, everything else is the same. It's not as easy plug and play, but I don't think that's the major obstacle.
All right, let me open up some questions. I kindly ask you to introduce yourself so that the speakers know. Sir, over to you.
David Wilcox, Reach Scale. So Lazard's reports 97 to 136 for nuclear, 50 to 60 for solar, 32 to 62 for offshore wind, 82 to 155, or 80 to 155 for offshore. Onshore is about the same as solar. If I understand correctly, if you build smaller power plants, there's no possible way you could have a lower cost per megawatt hour for the smaller plants.
That's not what I said.
For the big plants.
I said it's a question mark.
Well, everything I know about scale would suggest you could maybe match it, but you'd be really fortunate if you did. Solar is going to drop 60% in the next 10 years by 2030. So their number is going to go down to $25 a megawatt hour. And if nuclear meets through the small plants its current $80 to $120 per megawatt hour. The other alternative is to build enough solar capacity in most of the United States where you have lots of sunny days to handle the lowest, the least energy producing period. That does two things. It dramatically reduces the amount of base load you're going to need, and it enables you to have free energy during the day. You have massive overruns of the energy supply during the sunny part of the day, which can be deployed in a variety of ways to create value. And then you only use the storage, not for other parts of the day, but just for the night. You just use the storage for the night. Doesn't that just make way more sense than trying to magically get nuclear down to $100 a megawatt hour?
It's not magic.
So the answer is no. Let me challenge on many things that you said.
This is great. I think this is
starting with the expectation that that solar is going to drop even further. As you probably know, because I understand from the chat that we had prior to the panel, you're in the industry, you're in the solar industry. The amount of commodities that solar and wind, for what it's worth, use in terms of concrete and steel are orders of magnitude larger than what nuclear uses. So those commodities are becoming more expensive. So the expectation that magically solar continues to drop is a hope. A little bit like me saying that, yes, we hope that nuclear will drop. Having said that, the scaling question about nuclear, it's not a foregone conclusion that if you make a smaller machine, it's going to be more expensive than a larger machine on a per unit energy generated, because there are set points, there are discontinuities in the cost curve where you can go from, for example, active cooling to passive cooling and get rid of a bunch of systems. So there is design simplification that can allow you to actually not go down one curve, but drop it down. Now, the other point that you made is, sure, I'm all in favor. I think we should deploy as much wind and solar as we can. It's great, okay? But if you want to use all that extra energy that is generated during the day, et cetera, you have two alternatives. We have three alternatives. The first is absolutely not desirable. You curtail it. That's a waste, okay? Number two is you store it. Well, then I'm back to what I said earlier. In order to meet demand when that demand exists, you gotta overbuild first the capacity of solar and wind. Number two, the capacity of storage of the batteries that then will give you that energy when you want it. Number three, it's what you were suggesting. When there is excess energy, I don't store it, I use it for something else. Well, that sounds like a great idea. What do you want to use it for? You want to make hydrogen, for example. You want to make other liquid fuels. Great. How do you make hydrogen? You need electrolyzers. So then what you're telling me is that those electrolyzers are being used only when there is excess solar capacity. Well, the capital cost of the electrolyzers, all that infrastructure to make hydrogen is just sitting there doing nothing until there is excess solar capacity that drives. One way or another, you're overbuilding. There is no way around this issue of intermittency is the bane of solar and wind. They're great energy sources, but they're intermittent. There is absolutely no way around. Either you store, you do something else, you're gonna overbuild and underutilize. So when you look, so I'm back to the statement that I made earlier. When you look at an integrated energy system, having something like nuclear that gives you the energy that you want, one, carbon-free, two, when you want it, has enormous value. So that's how I would answer.
Thank you.
Really appreciate it.
But it's, I mean, you made a, I'm glad you brought it up, yes. But it's not as simple as
I think
everything with intermittence.
I think with your question, it's really important, especially for the students. We think too much only about the energy source, but it is really the infrastructure, the commodity markets, absolutely. All this ecosystem that comes with it that actually does require to sustain either solar or nuclear energy. So I think it's important we think about this ecosystem.
Backup.
Sure.
And also we should worry about reliability. So that's, the more integrated and the more interconnected the grid becomes, the more vulnerable it becomes. So this idea of having distributed energy sources that can actually provide energy more locally, for example, smaller reactors or smaller solar systems, et cetera, is actually good because it enhances resilience. But if I produce my solar in California and I want to use it over here, that means all that energy's got to come across the country on a transmission line. All it takes is someone throwing a nice little hand grenade at a transmission line, and half the country is now in a blackout. So not a very resilient, not a very robust system.
Other questions? Please. Oh, Do-young comes from a very interesting country.
Hi, my name is Do-young. I'm a second-year student at the Fletcher School. I'm from South Korea. So going back to Ukraine-Russia issue, what we have seen so far throughout the years that Russia weaponizing the nuclear energy sector, taking the Zaporizhia nuclear energy plant as a hostage for their purpose in the war. How do you see the situation, and do you think there are any frameworks or measures that the international community can take and address to prevent such rogue states using civilian nuclear energy sector for their own purposes that could harm not just the environment, but international security in general?
Is it for me or for her or both or either one, whoever wants?
Yeah, I don't know. I mean, in a war environment, I think you could use a lot of things as weapons, as pawns, and so it's a very difficult problem. not trying to minimize the issue, but I would hope that the international community, if Russia really does something with that power plant, they respond accordingly.
Yeah, I mean, I would agree that there is nothing the international community could. A country that invades another country, there is a nuclear power plant there. Now, that country that is invaded has control. So, what could we do? I mean, short of us moving in and pushing them back, or the Ukrainians pushing them back, now that nuclear power plant belongs to Russia until they decide to finally move the hell out. So, there is not much that we can do. The only good news I can tell you about Zaporizhzhia is that those 6 reactors have been shut down for 6 months. So, the decay heat is down to nothing. Radioactivity is very low, so there's not much damage that they can do at this point, even if they wanted. But it would be a shame. It's the largest nuclear power plant in Europe. It's a massive asset for Ukraine. Prior to the war, they drew some 20% of their electricity from that site. So I hope that, you know, when this whole hell is over, they get control back and they restart it in due time with the, you know, after they fix what has been damaged, shelled, whatever it is. So again, not a big risk at this point, radiologically, no, but certainly an office.
Hello, my name is Grace Hall, and I had a question or an idea related to fusion. My dream is that it will take a long time to get it really going, but say by 2050, maybe it would be up and doing really well. And at that point, because we will have been using materials to build the turbines, to build the solar panels and so on, we'll be using up a lot of raw materials. We'll recycle somewhat, but there's always waste. And we'll be using up those things. And then fusion could move in at that point and help long-term at a much more efficient way.
I'm a strong believer that we should look at the problem holistically, meaning you have to deploy everything we can. And so, yes, we might have a bias for a technology. I am biased for nuclear, but there is space for any technology that we can deploy and can deploy quickly. So yes, more solar, yes, more wind, yes, whatever we have available, let's use it. So I find that focusing on one particular technology is not the appropriate way of scaling up the need of electricity in general. And so yes, fusion will need some more time. I don't even know how expensive it will be at this point. And so if fission is a question mark, fusion is it's a double question mark. And so, and yes, in the fusion community, the joke is like when fusion is available, it's always 30 or 40 years away. I hope that this time is for real, and I hope we will be at the point. But I think materials, it's an interesting subject because a lot of people worry about, oh, we're going to deplete this particular resource, we're going to deplete this particular resource. It's all a stock market game, in my opinion. And so we'll always find a way of being more efficient. I'm not saying infinite amount of resource. We don't have infinite amount of resource. But I don't see any resources really dying off in the next 50, 100, 150, 200 years, because when the demand is going high, then the company are willing to maybe invest more money in getting material that before they were not bothered to take out of the ground because it was too expensive. So to me, it's everything is a little bit brought to this extreme of, oh, we're gonna run out of rare earth material, we're gonna run out of copper, we're gonna, I don't know. It's always this anxiety about we are gonna run out of everything. So.
I agree on the question of availability, that there is of materials, that when people look for new materials or more materials, they find them. The key question, I think, is gonna be twofold. First, cost, but number two, maybe a more important environmental impact, right? So sure. If you now have to dig out 300 billion tons of lithium or whatever it is, it's going to have a real environmental impact as opposed to, I don't know, 100,000 tons of something else. Right? So
I have to tell you, so I wanted to build on this great question because maybe that would make you really uncomfortable, Luisa. But for people like me who know very little about fusion, I have the luxury to believe that fusion is going to solve all our problems, right? I mean, we talk about nuclear fusion as this is it. When fusion arrives, all our issues are going to be gone. And then you sit here and you think, well, you know, this is not a big deal. It's just a different way to heat water and stuff. Do you see this hype about nuclear fusion? Is the idea that this is really going to be the global game changer?
I love to think that yes, but you know, we've been burned several times over even the last 20 years. And so I think, I'm hoping that it will play a role. I don't know how quickly it will play a role, but yes, it's a great, I think technologically it's very interesting. The engineering is very interesting. The physics is very interesting. So from a research point of view, it's like it's this wonderful machine, and you're like, oh, I cannot believe this is gonna work. How big of a role we will be playing, it will take time, and so I don't know. But I like the enthusiasm. I love the idea that everyone is hoping for fusion to become our solution. But we have to be a little more patient.
Yeah. Can I make a comment on this?
Yes, please.
So there is a difference between a prototype or a demonstration plan and a reliable technology that is scaled to actually move the needle and make an impact. Okay, so I am actually quite optimistic that the point you made, 10 years from now, we might even have a prototype, something that is producing electricity on the grid that is fusion-based. If my friends at MIT that you mentioned, Commonwealth Fusion Systems, are going to be successful, 2 years from now, we'll have an experiment that actually shows that you're getting more energy out of fusion than the energy input to make that fusion happen. That would be a little bit like the Wright brothers flight, you know, where you can sort of proof of principle that humans can fly. It's still a long way to the 747. Okay, so to a reliable airplane, but forget about 747, even a World War II airplane that is reliable, that is not, you know, tipping down every 3 weeks. Okay, so for energy technologies now transitioning to something a little bit closer, even nuclear reactors, when they first appeared and connected to the grid in the 1960s, they had abysmal performance. They had capacity factors of 45, 50, 60%. Guess where we are now? We got 92, 93 reactors in the nation, producing 20% of our electricity. They run like Swiss clocks. They have capacity factors north of 92, 93%. 92, 93%. That's reliability, okay? But it didn't happen overnight. And it had nothing to do really with the technology. It had everything to do with people becoming proficient at operating these complex power plants. So I expect a similar curve. Yeah. It's the 21st century. Instead of 20 years, maybe it's 10 years, but you do the math. So 2035, we got the first prototype. 10 years later, 2045 becomes reliable. Yeah. So to your point, 2050, this will be an industry. So, you know, good. But it's not tomorrow, right? So, yeah.
Thank you so much. It's been extremely insightful. I'm a first-year model student here. I'm focusing on energy and technology, and specifically work with energy issues. I was wondering, India is like kind of hyper-focused on research around thorium-fueled reactors, and I just wanted to understand kind of your understanding of what is the scope and feasibility of these. Do you think that, I think majority of the research and like resources are going into these, and I wasn't sure if, you know, India should be putting all their eggs in one basket.
Don't respond. I have another question on the back. Yes, sir.
I was going to ask, like, if we can't even build solar farms with permitting, like, how are you going to convince people to build nuclear power?
The question of NIMBY, right?
Yeah, you need less space, so maybe you find the backyard that it's the right backyard.
It's difficult to build anything anywhere.
Okay, thorium first, and then
we do thorium first, and then maybe you take the NIMBY. So at the moment, India has a nuclear capacity of 7 gigawatts. They are in the process of doubling that, 14 gigawatts. For reference, the US is about 100 gigawatts. So it's still a small industry in India, but it's growing. All the reactors are uranium-based. So for all the chit chat and hype about thorium, India is not using a single gram of thorium in the reactors. They're using uranium because it's an established industry and it works. Is thorium as some theoretical merits? Certainly. The main reason why India has always been interesting is because they have a lot of thorium, they don't have a lot of uranium, so it could become entirely domestically self-sufficient. But it's a headache, it's a higher cost, in my opinion, completely. I'm giving you just my, bare opinion on this. I think India should rather stick with uranium. Uranium is a commodity, is internationally traded. It comes from all over the place. If you don't like to get it from Russia, which by the way is not even a great producer, you get it from Kazakhstan, you don't like Kazakhstan, you get it from Canada, you don't like Canada, you get it from Australia, you don't like Australia, you get it from the US. There's uranium all over the place, Namibia, Niger. So it's not like, okay, you don't have to produce it domestically, you can just get it from the international market. So these sort of enamorment with thorium to me is a waste of time and money.
So let me build on this question about, what kind of permit can we get? There was a great article on The Economist that said, we are pursuing very conflicting goals. On the one hand, we need to decarbonize the economy. On the other, we also need to safeguard the environment. And so this question of not in my backyard, you can't build a nuclear power plant or a solar farm is becoming really important. So, I mean, it's a little bit of a dilemma. It doesn't have really a real solution, but how should we think about this?
I don't know. I think the solution should be you have to buy in the community support. As industry, you have to do much more work in actually giving back to the community that is willing to have a solar farm or a wind farm on their territory. And so to me, it's the work has to be done from the industry perspective in having a collaboration with the community and not just going in and saying, oh, we are going to build this, and sure, your electricity cost might be stable for 20 years, but there is no other kind of, they have to give a little more than just that. And in my opinion, that's how you build the community sense of, we're doing something together for the environment. And but yeah, it's very difficult. But the space you need for a nuclear power plant is much smaller than the space you need for a solar power plant, and even smaller than what you need for a wind farm. And so if you look if you can find online, there are different measurements, but it doesn't matter. The nuclear power plant is always a little square, and then you have solar, and then you have wind, that it's the biggest. But it's always surprising to me how there is resistance to this project. It really, it's something I don't understand completely.
I think community engagement that you mentioned absolutely key, regardless of the technology, for any project. It doesn't even have to be energy, a new factory somewhere. If you don't engage early, and the key word is engagement, not education. Well, all three of us are educators, but the idea of education is that I know what's right, and and I have knowledge, and I'm trying to transfer it to you. That's not what works. What works is I listen to what your needs are, what your concerns are, and then we together work to make sure that everybody's comfortable. So engagement is absolutely key. But let me make a point about support, and I'm going to make it specific to nuclear. It's interesting because in the United States, for the past 25, 30 years, if you look at the generic support for nuclear, has been actually pretty high, 55, 60%. Actually, now it's almost like an all-time high. It's about 70%. So for solar and wind, is astronomically high, 90%. But that's generic support. Do you like wind? Do you like solar? Do you like nuclear? Sounds good, right? but now we're going to build it in your town. That's when the issue. So this is a real issue, which is why engagement of the community is important. But for nuclear particularly, I would say for these new plants, I've been advocating, I think the industry gets it, build them at existing nuclear power plants, the sites. We already have 60 sites in the United States. And if you look at the support of locals, is very, very high. Very, very high, because they've been in that area for decades. They got their neighbor that works at the nuclear power plant. They get tax breaks. It's good for the local economy and all that. So they're comfortable with it. So in my opinion, we want to build 50 new nuclear power plants. Don't try to find new communities, new sites. Just build them where the then existing plants are, and you already have connection with the grid. You already have access roads, you already have administrative buildings. I mean, the synergies are enormous. So I think that's a way to sort of break in easily instead of saying, I'm gonna put one in Central Park. Right? It's not gonna happen.
So I need to close here, unfortunately. This it's only 1 hour we had, and I think you guys could see like there is so much interest in nuclear energy right now. Many years ago, it would have been very different,
It would
right?
have been different. Yeah.
And I think this is a great moment to learn more about these technologies. Please, if you guys can stay around for a few more minutes, I know some people have questions. Please join me in thanking Jacopo and Luisa for